The last colligative property that we have to talk about is something called osmotic pressure. So this is measured as the pressure needed to stop osmosis, which is a bit of a circular definition, but don't worry, I'm going to draw you a picture. We use this in a practical sense. Osmotic pressure is a thing that we care about in practical terms. It is used when looking at concentration in IV solutions and when thinking about laxatives. So this is something that gets used in a practical sense in the medical field. You probably have a good idea of the definition of osmosis, but I'm going to put it here anyway, so you have it all in one place. For osmosis, we're talking about flow of solvent through a membrane. To equalize concentrations. So in terms of what we would look at to measure something like osmotic pressure, I'm going to do my best to draw what this might look like. So it'd be some kind of container that has two chambers, and each one of them has, I don't know, like a neck or a piece that comes up to tell us about the level of the solvent or solution. And so these are divided. This would be the membrane. And on one side, we would have pure solvent. So I guess let me put this in blue. And on the other side, we would have some solution. And what would happen is that these would initially start with a solution at the same height. So I guess probably somewhere, I guess probably in the middle is where it would start. And let me put this down in words. So the solution, solvent, both start at the same height in terms of how we're measuring the volume on each side. So in a normal situation, the flow of solution would go from the right to the left. The pure solvent is going to flow through the membrane into the side that has the solution in an attempt to equalize the concentration. So flows right to left to attempt to equalize concentration. So this level would go down and this level would go up. So in the end, we would have some height difference that we could look at, right? This H. So this height difference relates to osmotic pressure. So essentially, essentially what we're saying is the amount of pressure that you would have to put down on this side of the solution to stop the solvent from flowing in, that's the osmotic pressure. Now, if you put more pressure, right, you could push it in the other direction and you could get the solvent to filter out of the solution to give you pure solvent. That's how reverse osmosis water filters work. But we're going to talk about just the amount of pressure that it takes to stop it. And we use a capital pi for osmotic pressure. So that is the pressure that we would be putting down on top of the solution side. So this equation is I times capital M, this is the molarity M, times R, which is the gas constant, and it's going to be the version that will give you pressure units, times the temperature. So M is molarity, well, we'll put the I in here, Van Hoff I factor. R, it's this 0.08206, right? Because if you look at liter atmospheres per mole Kelvin, what's the inverse of molarity and 1 over Kelvin? So we'll be left with atmospheres, which means our temp needs to be in Kelvin. Okay, so a lot of the problems will have you just calculate the osmotic pressure directly. The example that I want to show you, osmotic pressure is used for a lot of really large compounds, so things like polymers and proteins, to help you find the molar mass. So the example we're going to look at involves finding the molar mass of a protein. So this example says the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein in 10 mils of solution is 2.45 torr at 25 degrees C. Find the molar mass of a protein, and in case you need it, proteins are non-electrolytes. Okay. So we have the pressure in torr. We're going to need it in atmospheres. So that's one conversion that you can do. So if you want to pause and practice with the conversion, make sure you end up in the same place. It should come out to 0.00322 atmospheres. We know that the I factor is 1. We know R and we know the temperature. We need the molar mass, but that is kind of buried underneath the molarity calculation. So, let's just start by calculating the molarity and then figure out what pieces underneath we need. So we have pi, we have I, we have R, 0.8206. And the temperature, once we convert it to Kelvin, is 298.15. All right, so pi, 0.00322 equals I times M times R times T. So the molarity of this solution is 1.3176 times 10 to the minus 4th molar. So the molarity, so molar is really moles per liter. Well, we know the volume of the solution, so we could find out how many moles of protein were in the sample if instead of writing this as molarity, we write it as moles per liter. So it's equal to some number of moles, which we're going to solve for, divided by the volume, but we need it in liters, so 0.010 liters. So this means that the number of moles of protein in solution is 1.3176 times 10 to the minus 6 moles. Okay, well that's maybe partly helpful. If you look at the other information that you have, we know how big our sample was. So one of the ways to get moles is to take the mass and divide by the molar mass. So this 5.87 milligrams, let's write it as 5.87 times 10 to the minus third grams divided by whatever the molar mass is in grams per mole should equal the 1.3176 times 10 to the minus 6 moles. Now the other way that you can think of setting it up, which is the exact same math, is to say that 5.87 times 10 to the minus third grams per 1.3176 times 10 to the minus 6 moles gives you some value with units of grams per mole, which would be the molar mass. Now, in either case, when you do this calculation, the molar mass is equal to 4.46 times 10 to the third grams per mole. Now, this is a really big number, but that makes sense because proteins are really big molecules. So getting a large value for your molar mass here is a good thing.